There's another concept that is important and easier to talk about in the continuous case, although you can also talk about it in the discrete case. It's the idea of the joint probability distribution function. You assume here that you have two continuous random variables. X could be the height of an individual and Y could be their weight, for instance. On average, you would expect that if you know someone's height to be fairly tall, you might expect their weight to be larger than somebody whose height is short. So there's a correlation, if you want, between the two variables. At least it's conceivable that two variables would be correlated, even though at first glance they might have nothing in common. So a joint distribution talks about the joint probability of X being equal to something and Y being equal to something simultaneously. It's a joint probability density function or joint distribution function, a joint PDF, if it satisfies the three conditions here, which are basically the same conditions as what you would get for a single random variable. It's just been extended to more than one variable. I'm writing it here with two continuous random variables, but it could also be 3, 4, 5, any number of continuous variables occurring at the same time. The properties are simple. That function has to be non-negative for any point x and y, or potentially you could say that the function is strictly positive for any x and y in sample space. The full integral, in this case it's a double integral, though not just a single integral, has to be equal to 1. The probability of falling somewhere in the domain is 1. And the probability of an event, which is given in terms of specific values that x and y could be taken, that should be the integral of the joint PDF over the region A. So you get something presumably that looks like this. X, Y, perhaps these are the only allowable values. Like this, for instance. So instead of a curve over the real line, you can imagine a sheet floating over the XY space. And if you're interested, say, in a specific region A here, then you'd be looking at the volume of the corresponding prism over that region. That would be the probability. So it's not an area anymore. This probability of the event A, it's a volume. It's the same idea, you just need to know how to do double integrals or triple integrals, as the case may be. It's simpler to talk about continuous variables because we have a simple rule to go from the probability density function to the probability we integrate. When we're working with discrete random variables, we have to replace all of the integrals by sums. And typically speaking, double sums are just more time-consuming to compute than double integrals. There is one more difference if you're working with discrete variables, because then the value of the PMF, the joint PMF at any given point, tells you the probability for that specific combination of variables, and that means that the value of the PMF has to be smaller than 1, because the probability cannot be greater than 1. For continuous joint variables, that is not the case, right? So let me remind you here what this third property says. The probability of an event would be the volume of the solid over the region in the xy plane that's bounded by the surface given by the joint PDF. That's the drawing I tried to draw. It's the same idea as what happens when you only have one continuous variable. Here are some examples of joint probability density functions. Let's say you have a pair of unbiased dice. You roll them. There's 36 possible outcomes, right? One of them could be 1, 2, 3, 4, 5, 6, and then you use a counting principle. The second one could also be 1, 2, 3, 4, 5, 6. So you have a total of 36 different outcomes. Right? All of your outcomes will look like a number here for the first die and a number for the second die. So for any of these outcomes, X will denote the smaller roll and Y will denote the larger roll. How many of the outcomes correspond to the event that the smaller roll is 2 and the larger roll is 3? Well, you have 2 such outcomes. If you roll 3-2 or if you roll 2-3, then you're going to have that the smaller roll is 2 and the larger roll is 3. So that's 2 rolls out of 36. You would expect then the probability of that event to be about 5.5%, about 6%. 2 divided by 36. So we still compute probabilities the same way. This is a discrete case. We just count the number of favorable outcomes divided by the total number of outcomes. What's the joint probability mass function? If you roll the same value for both die, then you're going to be in the situation where X and Y have the same value. You roll 2 2s, X is 2 and Y is 2. So there's 6 different outcomes where X and Y are exactly the same. You roll 2 1s, you roll 2 2s, you roll 2 3s, 2 4s, 2 5s, and 2 6. For any other event, for any other combination of rolls, X will not be the same as Y. The lowest roll will be smaller than the largest roll. In that case, you have sort of 2 outcomes, right? X and Y and X would both give you the same X and the same Y. So the joint probability mass function is very simple to compute. It's going to take on the value 1 over 36. It's one of the 36 potential outcomes where the X and Y are equal. And in fact, there are 6 such outcomes. And you have the outcomes where X is smaller than Y. Well, there's basically 2 over 36 for each pair of X and Y. The first property automatically satisfied. This is always going to be greater than 0 no matter what. What's not written here but is implicit is that it's going to be 0 for everything else. What's the probability that the smallest value of the roll is 7 and the largest one is 9? That's 0. It's an impossible situation in that experiment. Now there's only 6 outcomes where you have X is equal to Y. If you roll 2 1s, 2 2s, 2 3s, and so forth. So the probability of rolling the same 2 values is 1 over 6. Because there's 6 such outcomes. So 6 times the joint probability, 6 over 1/36, that's going to be 1 over 6. And then the probability of having 2 different results. Well, there's 15 in total, right? You can say, I have the outcome of having rolled a 2 and a 3, and I have the outcome of having rolled a 3 and a 2, but they're the same outcomes because here X and Y don't measure which one was the first one and which one was the second one. It's basically measuring what was the smallest roll and the largest roll, right? So you have 36 total rolls that you can have, 36 total outcomes. 6 of those are outcomes where X and Y are exactly the same. 6 of them, and each of them has a probability 1 over 36. And 30 of them then have outcomes where the X and the Y will be different, but amongst these 30, every time you have one specific outcome, there's a corresponding outcome, which is the reversed one, which will give you the same X and Y values. And each one of these X and Y values has a probability of 2 over 36 of occurring. So you get 15 outcomes. The probability 2 over 36 for a total of, you guessed it, 1. If my previous explanation didn't satisfy you, think of it this way. X is the smallest value of the rolls. Y is the largest value of the rolls. X has to range between 1 and 6, but no continuous values, just discrete values. Same for Y. What's the probability that you would roll 2 1s? Well, that's one of the 36 possible outcomes. You get 1 over 36. So all of the entries on the diagonal, these correspond to the outcomes of the random variable where x is equal to y. They each have probability 1 over 36. What's the probability that the smallest roll is 5 and the largest roll is 1? That's 0. That's impossible. That doesn't match with our definition of what x and y are. So there cannot be any outcomes here, so their probabilities combined are 0. That makes sense. And then you look at all of the other potential outcomes. What's the probability that you would have smallest value of 1 and largest value of 2? That's 2 over 36, right? Because there are 2 outcomes that correspond to this. 2, 1, and 1, 2. So 2 outcomes out of 36. And that's going to be the case for every one of these values. If you add up all of these probabilities, you will get exactly 1. Now, can you compute the probability that x is equal to a or y is equal to b? What's the probability that the smallest roll, for instance, would be equal to 3? And what's the probability that the largest roll would be equal to b? Let's go back to the table for a second here. What you're asking is, what's the probability of having an x value equal to 3, for instance? And you look at all of the outcomes where the x was equal to 3. There's 1 over 36 when x is equal to 3 and y is equal to 3 when you're rolling 2 3s. And then you have the possibility of having rolled a 3 and a 4, a 3 and a 5, a 3 and a 6. These are the only ways in which your lowest roll can be a 3. You can't roll a 3 and a 2 because then your lowest roll isn't a 3 anymore. Your lowest roll is a 2. So if you add up all of these values, you'll find a probability of 7 over 36. These probabilities in the margin have a special name. We call them marginal probabilities. They're only applicable to instances where you have a joint distribution. Now, each of those is itself a probability density function. It has to be, right? If you have this as being x, x typically is given in relation to y, but x can be given alone as well. And so the value of all of these things here, when you add them up, that should be equal to 1. Because your x can take on the value 1, it can take on 2, 3, 4, 5, 6 with different probability. These are the probabilities for each of these potential values. When you add them up, you will get 1. Similarly, this y is a random variable on its own, so the sum of the probabilities that y take on all of its potential values has to be equal to 1. It's just that we get more information when we look at the joint probability density function. It is possible for y to be equal to 2. And it is possible for x to be equal to 4. We have values here, right? The probability that y is equal to 2 is going to be 3 over 36. The probability that x is equal to 4 will be 5 over 36. That's undeniable. But the probability that you will have a y equal to 2 and an x equal to 2 simultaneously, that's 0. That can't occur. So if we look at the joint distribution, we know more about the situation than when we look only at the marginal distributions. And you can do more as well. You can compute conditional probabilities. Like what's the probability that x equals 3 if y is greater than 3? What's the probability that y is smaller than or equal to 3 if x is greater than or equal to 4? These are conditional probabilities. We use the definition, right? The probability that x equals 3 given that y is greater than 3, we are looking for all of the instances among those instances where y is greater than 3 that x was equal to 3. So we've identified which regions correspond to each of the 2 events, the red region for y greater than 3 and the blue region for x equals 3, and we can compute the probabilities for each of these regions by adding up, all of the points in the red region for y greater than 3 and all of the points in the blue region for x equal to 3. will get as numbers 27 over 36 for the y greater than 3 region and 7 over 36 for the x equals 3 region. And now you're interested in the numerator region here, the region that corresponds to both x being equal to 3 and y being greater than 3. It's this region right here. That's what's both in the red and the blue region. And the probability of being both in the blue and the red would be 2 over 36 plus 2 over 36 plus 2 over 36. And that's 1/6. So what's the conditional probability that x would be equal to 3 if y is greater than 3? We look at 6 over 36, or 1 over 6 as the numerator right here. And the probability that y is greater than 3, 27 over 36, which is what we found, and you get about 22%. So what this is telling you is that if you know that the largest roll is going to be greater than 3, you have about 22% chance of having the smallest roll being exactly equal to 3. It's not the same thing as 7 over 36, which is the probability of x being equal to 3 specifically, because you have eliminated one option. You've eliminated the option that x and y could be the same. It is not part of that row. For the other one, what's the probability that you have both y smaller than 3 and x greater than 4? That's 0, because x has to be the smallest number, and so the conditional probability then is 0. If you know that your lowest number is greater than or equal to 4, what's the probability that your largest number would be smaller than or equal to 3? That's 0, it's impossible. Well, one question you might have is, why don't we just use the product rule to compute the probability that x is equal to 3 and that y is greater than 3? Why can't we just say, this is event A, this is event B, the probability of A and B is just the probability of A times the probability of B? We can't use that because we don't know if the events x and y are independent. We don't know that the probability that x is equal to x and y is equal to y is actually equal to the probability that x is equal to x times the probability that y is equal to y. Like, in fact, it's not the case with this specific distribution, because the probability that x is equal to 1 and y is equal to 1, that's 1 over 36, right? There's only one outcome where this happens out of the 36 outcomes. But the probability that x is equal to 1, that's going to be 11 over 36. We can see it right here. That's the probability of x being equal to 1. And the probability of y being equal to 1 is 1 over 36. And when you multiply these things together, you do not get 1 over 36. So what we would say here is that x and y are in fact dependent on one another. Not surprising, the lower roll you have will restrict the possible values that the larger roll can have. If the lower roll is 3, you cannot have a larger roll of 2. When the domain of the joint distribution function is not rectangular, then your variables cannot be independent. Be careful, it's not sufficient. You might have variables that are dependent in spite of the fact that they have a rectangular domain. It also depends on the values of the probability density function. Here's another example. Imagine that you have 8 similar chips. They're all in a bowl, but they've been marked differently. So 3 of them are marked 0, 0, 2 are marked 1, 0, 2 are marked 0, 1, and 1 is marked 1, 1. You select a chip at random, and you are given the sum of the two coordinates in dollars. So in 3 of the cases, you'll get nothing. In 4 of the cases, you'll get $1. And in 1 of the cases, you'll get $2. So what's the joint probability mass function of x1 and x2, where x1 and x2 here would be the coordinates? It is not too difficult for you to figure out that the joint probability mass function should be this quantity right here. Right? There's 3 chances out of 8 that you'll get 0, 0. If I replace x1 and x2 by 0, I indeed get 3 over 8. There's 4 chances out of 8 that I'm going to get 1, 0 or 0, 1. So if I replace x1 by 1 and x2 by 0, or the other way around, x1 by 0 and x2 by one, I'm going to get 2 over 8 for one of them, 2 over 8 for the other one of them. Add them up together and get 4 over 8. And finally, there's one chance out of 8 to get the 1, 1 chip. So 3 minus 1 gives me 1 over 8. So yeah, that makes sense. But I'm going to get the right distribution function here. What's the expected payoff? Well, you're looking for the value of x1 plus x2 on average. So you're looking at the expectation of x1 plus x2. And it turns out that you compute expectations exactly as you would in the case of a single random variable. It is going to be the sum, or the integral as the case may be, of the function of interest to you, the payoff, times the probability of having these x1s and x2s. Now we know what the probabilities are, like this: 3 over 8 for 0, 0, 2 over 8 for 1, 0, 2 over 8 for 0, 1, or 4 over 8 for, one of them being 1, the other one being 0, and then 1 over 8 for having x1 and x2 both being 1. These are the probabilities, and you multiply by the expected payoff for each of these probabilities. 0 in the first case, 1 in the second case, 1 in the third case, and 2 in the fourth case. These are numbers you obtain by just adding x1 plus x2. So the payoff is 75 cents on average. And so if you are offered the opportunity to play this game, but it costs you more than 75 cents to play, you shouldn't play it. On average, you will lose. And if you're offered to play this game and they charge you less than 75 cents to play it, then you should consider playing it. Let's do an example here with continuous random variables instead. You have 2 random variables, x and y, and they have a joint probability density function, which is a constant, 2. So any of the values of x and y are as likely to be picked if you want. But the domain of interest is not rectangular anymore. Your values of y have to be smaller than or equal to the values of x. That goes between 0 and 1. What's the support of this density function? It's the set where the probability is not equal to 0. So where is it that this probability is not equal to 0? It's for every x and y, where y is greater than 0, smaller than x, and x is smaller than 1. So whenever you look at these things, you look at the relationships one by one. So there's going to be one limit to the region, which is going to be given by y equals 0. Y equals 0 would be the x-axis. Then there's going to be one region which is given by the line y equals x. And then there's going to be a region given by the line x equals 1. Now, it's not clear, perhaps to you at first, where exactly you should be, but once you've drawn all of the lines, or the curves that are here, you'll see that there's only one possibility, right? Your values of y have to be greater than 0, so they have to be above the x-axis. The values of x have to be smaller than 1, so they have to be to the left of the line x equals 1, and the values of y have to be smaller than the values of x, so the height has to be smaller than the horizontal position, so you have to be here somewhere. And you're left with this region here. What's the probability now that the value of x you will have picked, if you're drawing variables randomly from that joint PDF, will be between 0 and 0.5, while at the same time the y value will be between 0 and 0.5. So you go back to the support, the domain of integration, and you're looking for the x values to be between 0 and 0.5, right? And the y values to be between 0 and 0.5. So you're looking at this square, but you know that can't be here. The probability in that region is 0. So the region of interest to you will be this region right here. That's your event A. I'll call this thing here A. So the probability of A, you're integrating the joint probability distribution function, over the region delimited by A. In this case, you need to remember how to determine this region. It's true that x goes between 0 and 0.5 and so does y, but it does so only in the red region. So what is that really saying? If you pick an x value right here, the corresponding y values have to go from 0 all the way up to x, right? Because this is on the line y equals x. So if x can be allowed to go between 0 and 0.5, the corresponding y values have to go between 0 and, well, they can't go higher than that. You could also see it the other way around. You pick a y value here that goes between 0 and 0.5, and the potential corresponding x values of points cannot go past 0.5, and they've got to be at least as large as y. Both of these represent the same region. Just if you're looking at them through a different lens. Well, I'll pick the one that we had done first. Here we have that x varies from 0 to 0.5 and y varies from 0 to x, and so the integral of interest would be this one here, right? This is the joint probability density function, and these are the integration boundaries for the event A. Right, you just do it as you did in calculus. The integral of 2 first with respect to y, that's going to be 2y, which you evaluate between x and 0, your upper limit and lower limit, x and 0, and then you will get here a function of x because you're replacing every y by x or by a constant, so that makes sense, and then you're integrating 2x between 0 and 0.5 as a function of x. Well, you'll get x squared, which you evaluate between 0.5 and 0, and then you're going to get 1/4. Not surprising here, if the PDF is constant throughout, what you're really asking is like what percentage of the area of the overall region is represented by this little triangle. And this, you see, it's 1/4 of the overall area. Now this approach only really works if the PDF is constant. Otherwise you have to do some other things. You can also compute marginal probabilities. What's the probability that x is equal to x? And what's the probability that y is equal to y? Well, these have to be functions of x and y separately. The probability that x is equal to x, you integrate over all possible values of y. Right? The result of this has to be a function in x. So let's integrate the PDF over all possible values of y. I write that y goes from minus infinity to positive infinity, but in reality y goes from 0 to x because anything below 0 has a probability of 0, and anything above x has a probability of 0 of happening. That's not part of the domain that we have here. And so we just need to integrate the function 2 and evaluate between upper limit x and lower limit 0. That gives you 2y. Between x and 0, that's 2x minus twice 0, 2x. So the marginal probability that x is equal to x if you know nothing about y is given by 2x. And similarly, the marginal probability that y is equal to y, if you know nothing about x, you're integrating the probability density function over all possible values of x, Well, x, as I've mentioned a few slides back, is actually going to vary between y and 1 whenever y is allowed to vary between 0 and 1. Right? If you go back to 1 and you pick a specific value of y somewhere here, the corresponding values of x have to go between y, right? If this is a value of y, this is also y and 1. So your x would vary here between y and 1. If you integrate, you will get 2 minus 2y. These are the marginal probabilities. And you can also compute the expectation of your random variables. What's the expectation of x? You need to integrate here, keeping in mind that you're working with the joint distribution function. You replace x by little x and f at xy by the value that it takes, 2. This is really the integral of 2x, x times 2, and then you integrate it over the region S, which as a whole, as we've seen, will be given by x going between 0 and 1, and y going between 0 and x. This is our domain. This is the integration order. You just do it one by one and you'll get eventually 2 over 3. So make sure you understand how to go from this to this quantity, which means you need to know how to define your domains of integration. You can do the same thing for the expectation of y. Replace x by y in here. And then you might find that it's easier to use the other definition of S, the one where y varies between 0 and 1, and where x varies between y and 1, in this case, because of the order of integration. Similarly, you'll get the exponential of y squared. It's 1 over 6. So really make sure you know how to do these computations. Are they independent? They're not independent because the support of the joint PDF is not a rectangular region. Now, being rectangular, as I said, is not sufficient, but seeing that it is not rectangular, they cannot be independent.